Hi, my name is Yuhsin Tsai from University of Maryland and is going to join University of Notre Dame as a faculty in summer. So it's nice to meet you electronically. And today I want to share with you a story about probing or determining the neutrino lifetime from cosmological data. Okay. And the talk is based on the paper I wrote recently with these people here. And we hope you will find these papers interesting. Okay. So I guess you don't need to see me now, but let me share the screen already. Let me do this. Okay. So of course, the story is about a neutrino, and neutrinos are the ghost particles in the Snell model, which we already know they exist. We produce lots of them every day in labs, but it's still very mysterious. Okay. Besides lots of interesting physics that we have learned about neutrino due to its very light mass and also a very weak interaction, and therefore the oscillation behavior becomes much more significant. We have learned a lot of physics on this front, but there are still many things about the neutrino that we just simply don't know yet. Okay? For example, we don't really know how long-lived can neutrinos be. Okay? It may sound like a weird question to think about, oh, how quickly will neutrino decay or disappear with certain times, for an elementary particle. It may sound like a weird question, but actually it is not, okay? It's a very legitimate question because neutrinos can decay as long as it has a mass, and we already know this, okay? So even for the simplest extension of the Snell model, where in which we just simply add a right-hand neutrino or add a Majorana mass term so that the neutrinos get a mass, the neutrinos can already decay through a loop level process into lighter neutrinos and photon. Okay. It's just that this decay process is super slow with the lifetime to be about 10 to 43 years. So the current constraint or the current sensitivity that's trying to look for the radiative neutrino decay is still far from this lifetime. That's why we haven't been able to see the neutrino decay in this radiative decay process. However, the radiative decay is not the only way the neutrino can disappear. Okay. In many of the other models, they're trying to generate the small neutrino mass. Neutrinos can decay into invisible particles, can decay into new particles that we haven't seen so far. Okay. So usually this type of models that generates the light neutrino mass comes with assumption that the reason why neutrino mass is small is because its mass is forbidden by some symmetry. Okay? So once the symmetry has a spontaneous symmetry breaking, the neutrino can turn on a small mass, and that's why its mass is much smaller than any of the other particles that we have been seeing so far. Okay? So usually this spontaneous broken of the neutrino symmetry that gives the mass will come with a Goldstone boson in these models. And this Goldstone boson is neutral, so it's invisible, we don't see it directly, but it can couple to different neutrino species and therefore induce a neutrino decay into lighter neutrino or Goldstone boson. Okay. Or in some of the models, the Snell model neutrino can also decay into the additional massless stereo neutrino and the Goldstone boson. Okay. So in terms of cosmology, this just means that in the late-time universe, neutrino can transfer its energy density into invisible dark radiation. And then we are interested in seeing what's the cosmological consequence of this. Okay. So this invisible decay can happen within the age of the universe time scale. Therefore, can in principle generate a sizable changes of the late time cosmology. Okay, so a few words about the neutrino mass. Okay. So we already know that cosmology observations, such as the CMB observations, has been able to set a very nice bound on the sum of the neutrino mass. Okay. And the current Planck data sets the mass to be about 0.2 EV scale, and including the BAO observation, we can tighten the bound to the 0.1 EV level. Okay, so this is a very nice constraint that we can get already from cosmological data. However, one thing I need to remind you is that when we set the bound, we already assume the neutrino is stable, at least in the cosmological time scale. And it will be interesting to know how would the bound change if neutrino does decay and have a finite lifetime. So let's just first take a look of how what's the existing bonds on the neutrino lifetime if they decay into invisible particles or into neutral particles that is not photon or not charged particles. Okay. So it turns out the bond is extremely weak. From all the long baseline neutrino experiments, the lifetime constraint that we can get is only of order 10 to minus 14 seconds. There's really no bound from this long baseline experiment. Okay. Even for neutrinos that is produced far away from a supernova explosion, for example, because the neutrinos are highly boosted from these astrophysical sources, the lifetime constraint is still very bad. Okay. That's why we only get the lifetime constraint to be about 8 hours for neutrinos that was produced from supernova. It turns out the tightest constraint we have now, again, already comes from cosmology. So if neutrino can decay and having its inverse decay during the CMB time, the neutrino would stop being free streaming particles, and therefore changes the damping and also the phase of the CMB spectrum at the high L modes. Okay. So people have been using this to set a lower bound on the neutrino lifetime, and which is only of order 10 years lifetime. So all of this is to remind you that it is extremely difficult to measure the neutrino mass in lifetime, especially when they decay into invisible particles. Then the question is that, can we improve these bonds? And also, is there a chance that we can see the neutrino decay? So in the end of the talk, I'm going to show you that we do have a good chance to extend this bond to 8 orders of magnitude using some of the near future large-scale structure survey or the weak lensing, the CMB lensing measurement from the future CMB experiments. Okay, so we do have a chance to extend the sensitivity of seeing the neutrino decay to the 10 billion years time scale, and that will be very, very exciting. Okay. And I also encourage you to take a look at this early paper by Serpico that also mentions a similar idea to probe the neutrino decay. If you are not a cosmologist, okay, it's just give you a very quick idea about the data. So the data I'm going to use to see the neutrino decay is a survey of the large-scale structure of the universe. Okay. So you can basically think this as the distribution of galaxies in the universe, which basically indicates what's the distribution of the cold dark matter and baryon is in the sky. Okay. And for the actual observation, besides looking at the distribution of the galaxy, we can also use the so-called weak lensing survey to map out what's a dark matter and the baryon distribution in our universe. So the fact that the cold dark matter build up the structure, so we have a not a very homogeneous distribution of the galaxy in the sky, tells us that the structure was formed, was built up, comparing to the CMB photon. And the fact that the neutrino carries the mass and can decay is going to change the structural formation and therefore changes this pattern of galaxy everywhere in the universe. Okay, so that would be the signal. Okay. So the way that the structure form is simply comes from the Newtonian physics. Okay, so during the matter radiation equilibrium time, for the location in the universe that has a slightly larger density of dark matter particles due to primordial fluctuation, it will attract more and more dark matter particle and baryons to fall into the same location, and that's how we build up the structures. Okay. So now if we add massive neutrino in this particle soup in the late-time universe, since neutrinos, even though they carry a mass, but because the mass is small, the neutrinos will flying around and only becomes non-relativistic at the very late time in the universe. Okay. So as a fact, the neutrinos will have a much more homogeneous distribution in the universe comparing to the cold dark matter and baryons. So that's why they don't directly contribute to the clumping of the particles, but what they will do is to increase the total energy density of the universe, increase the Hubble constant, and therefore shorten the time window between the matter radiation equilibrium and the size. I mean the time it takes the universe to expand to the size that we see today. So we get a shortened amount of time for the structural formation. Okay. So because of this, we end up having a smaller density perturbation for the cold dark matter, even if neutrino distributed homogeneously. Okay. So a larger neutrino mass gives a smaller density perturbation. The current sensitivity of the look for the density perturbation is of order 10% level, okay, comparing to what we believe it should be from the cold dark matter scenario. But soon we are going to have an order of magnitude improvement in the density perturbation measurement thanks to this near future experiment such as Euclid, LSST, and DAISY experiment. And many of them are going to launch and start to take it data very soon. Okay. So the further future observation from the CMB and from especially for the CMB lensing measurement is going to help us to improve the analysis also. Okay. Okay, so now what if neutrino decays into radiation? Okay, how would that change the structure formation? For all the analysis I'm going to show you, we are going to assume the neutrinos decay into massless radiation. Okay. So this is a nice assumption for models that the neutrino does decay into massless stereo neutrino plus the Goldstone boson I mentioned before, or if the neutrino have hierarchy follows the normal hierarchy, and when their mass is approaches the 0.1 EV, sorry, the sum of the mass approaches the 0.1 EV level, then we do have two heavier neutrino and one much lighter neutrino, and there's a good chance, and the results that I show you can also be applied. Okay, but no matter what's the hierarchy called mass that the neutrinos have, the main physics I'm going to tell you remains the same. Okay. So first, let's still start from the case when a comparison between the massive stable neutrino versus the universe that doesn't have a massive neutrino. Okay. So the way I show you the effect is to take a ratio of the density perturbation of the cold dark matter particles with and without a neutrino mass. In the early time universe, since neutrinos are still relativistic, this ratio is 1, but when the scale factor becomes larger and larger, the neutrino becomes more and more non-relativistic. I get a separation of the density perturbation, as I mentioned before. So you see the black curve goes down below 1 until the CC dominance universe. So now if neutrino decays at some point, it changes its energy density from matter density back into radiation density again. Okay. So in this case, the universe looks similar to the universe that has massless neutrino. Okay. So that's why once neutrino decays, when I take a ratio of the density perturbation to the massless neutrino scenario, this curve will get flattened. Okay, and it no longer decrease after neutrino becomes radiations again. Okay, so as you can see, both in the blue curve and the orange curve here, the curve begin to flatten out once the neutrino decays. So this behavior of the flattening of the curve due to the neutrino decay can be described quite nicely also from an analytical approximation that we derive in our first paper. Okay, so if you are interested in getting a quite nice estimate of the size of density perturbation for warm dark matter decay into radiation, for example, I encourage you to check our analytical expression in the paper. But for all the studies that I'm going to show you, we do things in a full numerical way. So the net effect of heavy neutrino to decay is that in the end, I'll get a larger density perturbation comparing to the stable neutrino scenario. Okay. So I do increase the size of the density perturbation, or I do get more structure than what I expected to have comparing to the stable neutrino scenario. Okay. So this is the effect of heavy neutrino to decay. So we get more structure. So maybe let me emphasize, this is one of the very few cases that we end up getting an increase of the density perturbation in the late time universe. And here we can simply have in that from neutrino decay. Okay, so it's a quite unique signature, I would say. So now let me just show you some results from the cosmological data analysis. Okay. So already using the current data from the large-scale structure survey and also from the CMB lensing analysis, we can already set the bounds on the neutrino mass and lifetime. Okay, so which shows up as in the plot that you see. Okay. So the preferred neutrino lifetime and the mass will stay in this blue region, and the red contour behind is just a result that without including the large-scale structure survey. So it looks like the Planck result already sets a pretty nice constraint so far. Okay. So one thing that you can see immediately is that there is a shape on the boundary that goes up, tells us that in the upper part of the plot, that tells us that we cannot distinguish the scenarios that have a heavier neutrino mass and a shorter lifetime. Okay. So it looks like the data doesn't really set the upper bound, lower bound on the neutrino lifetime, but instead leaves us a degenerate relation between the mass and lifetime. And it is easy to understand this. Okay. So now if you can see the plot on the right and look at the black curve versus the red curve. So the black curve here shows the similar density, the ratio of the density perturbation with a massive and stable neutrino, okay, as a function of the redshift. So if you look at the result of the low redshift in this black curve, where we get the suppression, the same result can be faked by an unstable neutrino scenario, which has a heavier mass but a shorter lifetime, which is the red curve in the plot. So we only get to see the universe at low redshift. We won't be able to distinguish these two scenarios. So that's why there's a degeneracy between the mass and lifetime that we cannot break if we only see the sky today. Okay. But even with this degeneracy, we can already see very interesting physics here. Okay. For example, the current result tells us that neutrino can actually be as heavy as almost 0.8 eV scale, as long as it decays before the age of the universe is 10 million years scale, okay, basically. And this is extremely interesting when thinking about a comparison to the direct neutrino to experiment that's trying to measure neutrino mass directly. Okay? Because usually this experiment has a sensitivity, or I should say the expected sensitivity, to be the sum of the neutrino mass to be of order 0.6 eV. If you compare them directly to the existing constraints from the CMB, those sensitivity are not very interesting because it's already way beyond the current constraint of the neutrino mass. Okay? However, if neutrino is unstable, you do have a chance to have heavier neutrino that can show up in these experiments as long as they decay quick enough. So this gives a very interesting interplay between the cosmological constraint and this future neutrino mass measurement experiments. So this is the current status of the lifetime mass constraint, as I showed you before. If you want the neutrino mass to be heavier than 0.3 eV scale, you would like them to decay before 100 million years. That's the current constraint. But this is not a very satisfying result, right? Because it tells us that due to this degeneracy, we still cannot measure the mass and lifetime independently. And we also cannot make a statement to say if neutrino decay in a late-time universe or not. We won't be able to see it. Okay, so how are we going to resolve this? So it turns out there is a chance that we can measure the mass and lifetime independently and even determine the neutrino lifetime, okay? Which is to use the tomographic survey that many of these future experiments are going to have in the large-scale structural measurement. Okay. So even though this is the same plot I showed you before, even though I cannot distinguish the black curve and the red curve at low redshift, if any of this experiment can look for can look at the universe in the higher redshift, such as a Euclid experiment, it can has a chance to reach the redshift to be around 2. I can still see the different evolution of the density perturbation between the black and red curves at the higher redshift. So the difference between the two curves, at least for the example I show you, can be of order 0.5% level. And this will be within the expected, will be larger than the expected sensitivity of the large-scale structural measurement from the Euclid experiment. So we do have a chance to tell the difference between these two scenarios and break the degeneracy. So using this, we can generate some fake data with and without neutrino decay and see if the expected sensitivity from Euclid, and also including the existing CMB data, and to see if this data can distinguish this different fake CMB and power spectrum that we generate. Okay. So if we can distinguish the two scenarios, that means we can set the upper bounds on the decay rate of neutrino or lower bounds on neutrino lifetime. In terms of depending on the mass hierarchy of the neutrino and the sum of the neutrino mass, we can set a lifetime bound between about 1 billion year scale to the 10 billion year scale lifetime constraint. So this is what I told you before, that we can extend the lifetime constraint all the way to the billion years time scale. So it's an 8 orders of magnitude improvement. Even if neutrino decays, okay, if it decays around a billion year scale, we do have a chance to measure, or at least to constrain its lifetime window. Okay, so here are the two examples I show you, and the plot on the left assumes the sum of the neutrino mass to be about 0.25 eV, and the mass on the plot on the right assumes the sum of the neutrino mass to be 0.15 eV. And in both of these cases, we can have a hint or a measurement on the lifetime window within an order of magnitude variation. Okay, so this is extremely exciting because this is will be the only chance that we get to see invisible neutrino decay. So let me summarize. Okay, so the near future tomographic survey on the large scale structure can constrain or even measure the neutrino lifetime to billion years time scale. Okay, so I leave some of the conclusion plot here, and we can discuss more during the discussion time. Okay. Thank you very much.
Just a moment.
Sorry.